So let's get started. As I mentioned, the topic of today's webinar will be a deep dive into PTP, more specifically version 2. What is PTP, or Precision Time Protocol? How can I use it? Why is it important? How does it work? These are all topics we will cover today. As I mentioned already at the very beginning, I'm Stijn, Product Manager for Luminex. What will be the structure of today's webinar? We will say, as I mentioned, why is precision timing important for audio and video applications? What exactly is PTP? What are the fundamentals, the fundamental mechanisms behind the protocol? What parameters can I control? Why are switches important for PTPv2? And finally, we will see how you can configure and monitor PTPv2 in the GigaCore software, RNAO GigaCore software. So first of all, why is precision timing important for audio and video? This will be a copy of last webinar's presentation. So there we talked about the importance of audio, but they apply to video as well. First of all, you need an accurate and stable clock reference. This is such that the source of the video or the audio and the receivers all have a common time. Next, it's also important to have low latency for the small presentation time, especially in live applications. Multicast data distribution ensures efficient bandwidth usage. Data types need to be prioritized accordingly. High priority data such as clock, audio, they need to get a high priority in the switch such that they arrive with low jitter and a low presentation time at your destination. And finally, as with all protocols, you need sufficient bandwidth for all your data. Make sure that your link capacity is high enough. But the topic of today's webinar is, of course, the first item: how do I get an accurate and stable clock reference? Before we dive into that, let's explain the difference between latency and presentation time. So here on slide, you see an example with a microphone, a speaker, and 3 switches. The microphone and the speaker will get a common time source. The exact time value is not that important. They can both think that they are in 1995, but they need to have the same time source, the same time value. If you would be syncing multiple networks across the globe, for example, together, then it can be interesting to use a GPS time clock, such as a device from Mindberg or Brainstorm, such that these different venues all have the same time value. Next, the transmitter will timestamp the packets as they go out of their network port, and it will also somewhere will be defined a presentation time offset from that current time. So the transmitter timestamps the current time and sends the packet. It arrives at the receiver, but with a certain latency. So that's the time it takes to get all the data through the network to the speaker side. But the speaker will not immediately output this data. It will wait until the configured presentation time before the data will be played out. So it will buffer it for a moment before playing it out. So here you can see why latency and presentation time are different. Of course, it's important that all devices, all speakers have the same time reference, because if you have multiple speakers in the same room, you want them to play out audio at the same time. Otherwise, you get audio artifacts, and that's not nice. So next up, what is PTP? PTP is a precision time protocol. It's a protocol used for making sure that all these clocks in the network are synchronized. Where is this used? In finance applications, where timing is very critical, and they want to ensure that everyone is on the same time reference. The same applies to telecommunications and electrical power distribution. But of course, we are interested in the AV networks. PTP is used in AES-67, in Ravenna, ST2110, for Riddle Bolero, also for Dante, where they use PTPv1, and other protocols, other applications as well. But who controls PTP? PTP is an IEEE standard, and the first version came out in 2002, so PTPv1. This is, for example, still used for Dante audio. PTPv2 came out in 2008. It's used by ST2110 and AES67, but it's not backwards compatible to PTPv1. You can consider it two separate protocols, and if you want to sync them together, something in the network needs to translate from one version to another. Finally, there is PTPv2.1, which came out in 2019, and that's backwards compatible to PTPv2. There's some optional new improvements in there, like, for example, the possibility to protect or authenticate your grandmaster clock. Today, we will focus mainly on PTPv2, because we believe that that's the most important PTP standard currently in use. So what terminology should you know when we talk PTP? First, there is a grandmaster clock. The grandmaster is like your root timing reference. It will define the exact time in the whole network or in your time domain. Next, there are ordinary clocks. An ordinary clock can either be a time source or a destination for a synchronization reference. If it's a source, we talk about time transmitters, previously called master. If it's a destination, we talk about time receivers, previously called slaves. This new terminology was defined in Amendment G to the IEEE standard, where they considered new inclusive language. If you want to learn more about this language, you can visit this Meinberg article, blog post about the inclusive language and why time transmitter and time receiver are more appropriate. I will try to make sure that we use this new terminology in this webinar. It's also already in use by our software, but you can find the old master and slave terminology in many other applications and many other devices. Just know that they are exactly the same thing. Next, you can encounter boundary clocks. A boundary clock has multiple network connections, and it can sync one connection, so one network segment to another segment. So one port of the boundary clock will be a time receiver. It will get time from a path towards the grandmaster, and it will distribute this time again on all other ports as a time transmitter itself. The boundary clock will also sync an internal clock to the time transmitter. That's upstream. Next up is transparent clock. In this mode, the switch or the device does not take actively part in the protocol. It will just modify a correction field inside the PTPv2 messages as these messages pass through the switch. We will see in a moment how this all works and what exactly is going on. So here is an example of all this terminology combined. At the top, we have the ordinary clock, which is the grandmaster. That grandmaster is currently acting as a time transmitter. On the left side, we have a boundary clock. That boundary clock on the port towards the grandmaster is in the time receiver state, and the boundary clock will sync its internal clock to this time transmitter to the grandmaster. Next, it's distributing the time again downstream as the time transmitter itself towards two separate ordinary clocks that are in the time receiver state. On the right side, we have another switch. That switch is in the transparent clock state, so it's not actively syncing an internal clock to the time, but it's modifying the packets as they pass through the switch in both directions. It will update the correction field in there to make sure that the time receiver gets an accurate time reference of the time from the grandmaster clock. So we know what devices are taking part in PTPv2, but how does this work? Because it's a little bit more complicated than just standing next to each other and syncing your watch to the same time. So there is a time transmitter. You will send out, it's currently 10:15, for example, it will send out the exact time value. But it will take some time for this message to arrive at the time receivers. It will have a certain delay. So the receivers, their clock is running at a certain offset, not at the exact right time value. They will receive a message, it's currently 10:15, but they need to add a certain delay. And they don't know that delay, so they cannot immediately calculate the right time value at the moment that that message arrives. Therefore, a collection of different messages is being used in the PTP protocol. The first important group of messages are the event messages, where timing is very critical, and therefore these messages need to be time-stamped. The first message type is the sync message. It goes from the time transmitter to the time receiver, and it will contain the current time value. Next is the delay request message that goes from the time receiver to the time transmitter. And it's basically a question, what a method to measure the current delay from the transmitter to the receiver and the other way around. There are also general messages. The exact timing is less important, so they don't have to be time-stamped. The first is a delay response. It's a response from the time transmitter to a delay request. And of course, that goes from the time transmitter back to the time receiver. In a two-step operation mode, and we will see in a minute what that means, there will also be follow-up messages. Follow-up messages come after a sync, and they also go from the time transmitter to the time receiver. We will see later on why follow-up is sometimes used, or the two-step operation is sometimes used. So let's visualize all this. On the left side, we see a time transmitter. On the right side, a time receiver. And as we go from top to bottom, the time that goes up. So first, it's important to know that the time receiver is, of course, not exactly synced to the time of the transmitter. It's running with a certain offset, and the whole goal of PTP is to get this, to know this offset, such that the time receiver can update its own clock with this offset and sync to the time transmitter. The time transmitter will send a sync packet, and it will include in that packet a time value, which we will call T1 for now. This goes to the time receiver, but it does not arrive immediately. It will arrive with a certain delay. So by the time it arrives at the receiver side, it will get a timestamp, and the receiver will note down T2 prime, which is the equivalent of T2 on the time transmitter side, but again with a certain offset, because its clock is not fully synced. Next, it will transmit a delay request message at the time T3 prime, and the time transmitter, after it arrives with a certain delay, will note down the Rx timestamp value T4. Finally, it will transmit this value T4 back to the time receiver in a delay response message. So when that delay response message arrives, the time receiver has 4 different values. It knows T1, which was in the sync packet. It knows T2 prime, which is the time at which the sync packet arrived. It knows T3 prime, which is the time at which the delay request message was sent. And finally, it also knows T4 prime, the time at which the delay request message arrived at the time transmitter side, which was put into the delay response message. So a brief warning, we will now dive quite deep into the math on how we can convert these 4 values into an offset value. If you are not that interested into the math, feel free to skip a few minutes, but we believe that it's quite useful to know what's going on, why it's going on, and especially what assumptions are being made, because that will help later to understand why PTPv2 is important for switches. So a first assumption is that the delay is symmetrical, which means that the delay to send a packet from the time transmitter to the receiver will be equal to the delay to send the packet from the receiver to the transmitter. If we can assume that, then we can calculate the average delay so we have a delay here to send the sync packet, and a delay here to send the delay request packet. To send the sync packet, the delay is T2 minus T1. To send the delay request packet, the delay is T4 minus T3. If we average that out, we get this value. But the time receiver does not know T2 and T3. It also only knows T2 prime and T3 prime. So how can this be converted? We can say that T2 equals T2 prime minus the offset. It's just a conversion from the equation on the other side. And then we can fill in these values in the first equation, and we get this. So now we have T2 prime and T3 prime in the equation, but the offset is still there. And we don't know the offset, so we would like to get rid of that. How can we do that? Since this on one side is minus the offset, and here we have 2 times minus, which becomes a plus, the offset goes away because it's minus the offset plus the offset, so the offset can go. And then this can be simplified again to this equation, which looks almost the same as the first one, but now with the 4 values that are known by the time receiver. So at this point, we know the delay, but we still don't know the offset yet, which the time receiver needs to know to adjust its own clock. So again, we know the delay. We know that T2 is equal to T1 plus the delay. So we can fill in T2 here, and then T1 plus the delay, and then the offset. So T2 prime is T1 plus the delay plus the offset. In the next step, T1 moves to the left-hand side. The delay is filled in, and we get this equation. Again, some more mathematics magic. We take brackets around what's already on the left, and we move the other part also to the left side and cut it up a little bit, and we get this. And if you look closely, we see that this is basically 1 time T2 prime minus T1 minus half of that same value. So we get half of that value, and then the other side, T4 minus T3 prime, that also gets a subtraction. So then we get here. And we can rewrite this as this value, this equation, a very simple calculation that the time receiver can use with the 4 timestamp values that he knows to calculate the offset. When the offset is known, of course, it can adjust its own clock to match what it thinks that the time transmitter's clock is currently at, and the 2 devices are in sync. So next up, 1-step versus 2-step operation. It was already briefly mentioned when we talked about follow-up, but as you have seen, the time transmitter needs to put the transmit timestamp T1 into the sync package. It's like going to the postal office and right before you send a letter, opening it back up and writing the exact time that you are posting the letter at the office into the letter and then closing it back up. That's not an easy operation, and therefore the time transmitters can run in 2 separate modes. In 1-step mode, it will do everything in 1 step. There are no follow-up messages needed, and it will do exactly this. It will put the timestamp value T1 directly inside the sync messages. In 2-step clock mode, 2-step operation, it will not do that, but instead of putting the timestamp value T1 directly into the sync message, it will send out the sync message and then follow up with another packet, another message, and put that value T1 into that message. So what does this look like? With 1-step value, which we have seen before, it's quite easy. You get the timestamp T1 and put it directly inside the sync packet and send it to the time receiver. The time receiver will know the value T1 immediately when the sync packet arrives. In 2-step operation, the value T1 will not be put into the sync packet. So when the sync packet arrives, the time receiver only knows T2 prime, but not yet the value T1. this will be put in a separate packet and a separate message, the follow-up message. So only when that message arrives, the time receiver will know the value T1. That's the difference between one-step mode and two-step mode. So two-step mode requires an additional message, but it does not affect timing accuracy at all. In the end, the time receiver knows exactly the same values. A small recap, which message type have we handled? First of all, there was the sync, which goes from the time transmitter to the time receiver, and the sync message contains the current time. Next up, there was a delay request message going from the time receiver to the time transmitter. Also, an event message where timestamping was important. And then the second group was the general messages. So the delay response from the time transmitter to the time receiver with some time information about the delay request. And finally, there was the follow-up message, which is used in two-step mode to transmit the time value T1 after the sync message. There are more general messages, most important one being the announce message. The announce message is sent by all devices that can become grandmaster in the network. It's a multicast packet, so it will go through the whole network, and it advertises for each device their clock quality and priority values. And these parameters will be used by the best time transmitter clock algorithm, previously called BMCA, best master clock algorithm, to calculate who will become the grandmaster in the network. It's an election process. It's good to know that there are other messages, other general messages for management and signaling. These are mostly optional and often not that important. So how does this best time transmitter clock algorithm work? The grandmaster election process will look at these 7 parameters that are currently on screen, in this order as well. So first of all, there is the priority 1 value. Next up, there is the clock class and clock accuracy value, and only after that, it will look at the priority 2 value. Finally, there are parameters to match up if all before are the same, like clock identity, the port number on which the timing information was received, and how many steps the grandmaster is removed from that port. So as already mentioned, as long as all values are equal, the devices will continue looking at the next parameter. If values are different, then the lowest numerical value will win the election. So this means that the lower priority 1 value means actually that it's more important than the other device. If you would like to see more information about this algorithm, then you can check out this blog post from Mindberg with the URL currently on screen. Some examples. So we have 2 candidates to become the grandmaster that are displayed side by side, candidate 1, candidate 2, and all with their various parameters. As mentioned, they will look first at the priority 1 value, and in this particular example, this value is already different, so then the lowest numerical value will win the election, and therefore candidate 2, 10, is lower than 128, will win the election and will become the grandmaster clock. Here's another example. In this case, again, they will look first at priority 1, which is the same value. Next up, clock class, again, the same value, but then the clock accuracy is 1 on the candidate 1 side, which is definitely lower than the value for candidate 2, so candidate 1 wins the election. In this order, you can see that priority 1 is the most important value to control who will become your main grandmaster. Priority 2 is less important, but you can also see that if all priority values and clock class and clock accuracy values match, then the device with the lowest clock identity will win the election, and that's mostly determined by the MAC address of those devices. So most of the time, the device with the lowest MAC address will win the election if you don't configure any priority values, and these devices all have the same clock accuracy and clock class. So next up are PTPv2 parameters. What parameters can you control in your network to manage PTPv2. Here you can see a screenshot of the options that are available on gigacore switches. First, there is the domain value. The domain is like the time domain, and all devices need to be in the same time domain to be able to talk to each other. If you use different time domains in the network, then these cannot cross and they will not sync together, so each time domain will be handled separately. Next up is the announce interval. So the announce interval defines how many times a grandmaster-capable device will send out an announce message. It's most often set as an integer value, which needs to be converted to seconds using the logarithmic function. So if you set a value 1, you need to do 2 to the power 1, and you get 2 seconds. In our interfaces, you always see, therefore, a value between brackets, which is the value in seconds. Next up is the announce receive timeout. It's the amount of intervals before the device will consider the grandmaster as being lost. So if for 3 consecutive announce intervals no announce messages was received, then the device will consider the grandmaster as being lost, and the grandmaster election process will start over again. Next is the sync interval. It determines how often a sync message is being transmitted by the time transmitter. Again, this is a logarithmic value, so we need to convert it to seconds. That's also why it can be a negative value, for example, because 2 to the power minus 3 results in 125 milliseconds. So this means that with this particular configuration, the time transmitter should send 8 sync messages every second. And finally, there is the sync receipt timeout. Again, the number of sync intervals before the grandmaster will be considered lost. So could you change these parameters? If you reduce the announce interval, then it will take less time before the grandmaster is considered lost. But if you do it too often, then you send a lot of packets in the network, but also the grandmaster might be considered lost too soon. With the sync interval, a higher rate of sync packets will result in more accurate timing because the devices will update their internal clock more often. But it will also result in more load on the grandmaster because the grandmaster will need to handle more delay request and response messages. Of course, all these parameters, it's a bit complicated. To remember all of them, make sure that all devices are using the same parameters. So therefore, there are some profiles defined. These are a predefined set of parameters, often used for specific applications, and they help to make configuration easier and make sure that everything is interoperable. You can see the profiles that are supported out of the box by gigacore switches on screen now. So these are all various documents, various standards that define the protocol, the profile, and their values being used. If you really want to, you can also define a custom profile in our gigacore switches. So now that we are talking about switches, why are switches important for PTPv2? Let's consider a first example where the switch does not know anything about PTPv2. So either PTPv2 support has been disabled or it's not supported by the switch at all. We have a time transmitter on one side and the time receiver on the other side. And as we have seen before, the time transmitter will send a sync packet. It will arrive at the switch, where it will get buffered for some amount of time before going out to the time receiver. That one will send a delay request. Again, this might get buffered, but maybe less. Less time than the time transmitter's sync packet was buffered inside the switch. So if you remember correctly, if you remember from when we did all the math, one big assumption for PTP was that the delay is symmetrical in both directions, which in this example was definitely not the case because the delay request came through much faster to the left side than the sync to the right side. Finally, there is the delay response, but this is a general message, so timing is less important for the delay response. So if a switch does not support PTPv2, then this can cause high PTPv2 clock jitter due to the variation that the time spent inside the switch, the residence time. This variation can result in an asymmetrical delay and therefore a bad calculation of the offset value, and that will dramatically reduce the PTPv2 clock stability. In the end, the performance of this type of network will be very similar to PTPv1 performance, because in PTPv1, the switches also don't take part in the protocol. So what can we do to address this problem? We can put the switch in PTPv2 end-to-end transparent clock mode. When the switch is in end-to-end transparent clock mode, it will timestamp the incoming packets, so the incoming event packets will get an RX timestamp. It will remember when did this packet arrive at my ingress port. The packet will spend some amount of time in the switch to get propagated, and again, it will get a timestamp right before it exits the switch, right before it's being transmitted on the egress side. Based on these timestamps, the switch knows how much time the packet spent inside the switch, so the residence time, and it will update the correction field inside the sync packet with this residence time value. So the packet, together with the updated correction field, will arrive at the time receiver side, and the receiver can take this correction value into account when doing all the calculations. The same applies in the other direction for the delayed request message. It will also get an RX timestamp and a TX timestamp based on which the device can calculate the residence time and update the correction field. Finally, there is the delayed response, a general message for which timing is less important because it just contains the value T4, if you remember from before. But the timing of this packet itself is less important. So what can we remember from this mode? The switch will modify the event message packets with the correction field. In that value, it will put only the time that the packet spent inside the switch. This correction field is then used to correct the message delay with the accumulated residence time. So if you put multiple switches behind each other, then they will all add up the correction. They will not override the connection, but always add up. So in the end, you get an accumulated residence time inside the switch. This greatly improves the clock accuracy compared to having no PTPv2 support in the switches at all. So that's why it's very important to have PTPv2 support in your switches. Finally, in this mode, it's still important to know that all time receivers will talk directly to the time transmitter. If you have a lot of time receivers, a lot of devices syncing, then this can overload the grandmaster because it needs to handle all these delayed response messages. So we can move to peer-to-peer transparent clock mode. In peer-to-peer mode, again, a sync message comes in from the time transmitter. It will get time-stamped, like we have seen before on the ingress and the egress side. But now the correction will not only contain the residence time, but also the P delay of the previous link, the previous connection. So how much time did the packet spend to get from the time transmitter to the switch? This will get updated in the correction field. But how did the switch know that delay? That's done with P delay messages. So in every connection, the time receiver will send a P delay request to which the time transmitter will respond with a P delay response. That's happening on every link. So in the end, the switch will modify the packets exactly like we have seen with end-to-end mode, but not only with the residence time, but also with the P delay of the ingress side. This correction is used in the exact same method, and this time receiver will immediately know the total delay because it doesn't have to do any delay request and delay response messages anymore. This again improves accuracy compared to having no PTPv2 support. And also the time receivers don't all have to send delay request messages to the time transmitter. Only the direct connections to the time transmitters will need to do that. But it's very important that all switches in your network and all devices operate in this peer-to-peer mode and all have the same configuration. This makes this a very hard protocol to configure and troubleshoot. So again, a side-by-side comparison. On the left side, we have end-to-end mode, where all packets travel end-to-end from the time transmitter to the receiver, both the sync and delay request and response messages. The switch will update these with the correction field, which is the internal residence time. In peer-to-peer transparent clock mode, only the sync messages goes end-to-end, and on every connection, the peers of that connection, so the switch on one side to the time transmitter, and again on the egress side to the time receiver, they separately calculate the peer delay value with the peer delay request and peer delay response. The next mode is boundary clock mode. If the switch operates in boundary clock mode, it will also update an internal time reference. It will take part in the protocol itself and update its internal clock. So again, we have a time transmitter on one side who is sending out syncs, and the switch will now, on that link, act as a time receiver itself. So there will go a P delay request, a P delay response, and the switch knows its offset and sync its own clock, internal clock, to the time transmitter. Next up, this value is used on the other sides, on the downstream sides, to do exactly the same thing and make sure that the time receivers downstream use the same time reference and can also update their clock. This time, this is done to the clock of the switch, which in turn was already synced to the clock of the time transmitter upstream of the grandmaster. So switches in this mode take part in the whole message exchange. The port towards the grandmaster will become a time receiver port. The switch will sync its internal clock to this upstream time transmitter. And the ports downstream towards the time receivers will act as time transmitters themselves and will be the time reference for these downstream time receivers. This dramatically reduces the load on the grandmaster because not all time receivers have to send all packets back up to the time transmitter. They can just sync to the first boundary clock, and that's it. Only the boundary clock needs to talk upstream to the next time transmitter. It's good to know that all gigacore switches support boundary clock, and they even do that in every group. So in every VLAN, you can have boundary clock support. Finally, these switches also support replicate clock mode, which is very similar to boundary clock, but now we will replicate across different groups. So in this example, in the green group, there is my grandmaster. The group is configured as the boundary clock in this as a boundary clock mode. So the switch will update its own clock to that green grandmaster. This is exactly like we have seen on the previous slide with boundary clock. But now that time reference can be used in another group, so in another VLAN, to use the timing value there. And this doesn't have to be the same profile. It can even be a different clock profile, a different set of parameters. In this way, you can sync multiple groups, multiple VLANs, to the same time reference. This means that you can have different applications, all having the same time reference. And you can also put your grandmasters in a dedicated clock group, which kind of protects them. So here's another example. In the green group, there are the grandmasters. You can have multiple, and they will handle grandmaster election to the best time transmitter clock algorithm. There are no other devices in here, so nothing is sending any audio or video. These devices are put in a separate group. So the blue group will replicate its clock from the green group and then act as a time transmitter towards the Ravenna devices, and the same goes for the Riedel-Bolero devices in the pink group. So finally, a comparison of all different modes. We have seen how PTPv2 results in bad clock accuracy. Of course, it's very easy to use because you don't have to configure anything, but bad clock accuracy will be the result with possible artifacts on your audio or video streams. There is end-to-end transparent clock mode, which results in very good clock accuracy. It's very easy to use, but because you almost don't have to configure anything on your switches. But scalability stops somewhere because all time receivers will talk directly with the grandmaster clock. So therefore, this should only be used in small to medium networks. If you have a lot of PTPv2 devices, you can use peer-to-peer transparent clock or boundary clock mode, where boundary clock mode is definitely easier to use and more forgiving, while still resulting in the same clock accuracy. Boundary clock can scale very well in large networks, and it can also be mixed. You can have a mix of boundary clocks and end-to-end transparent clocks in the same network, and the boundary clocks will separate the networks in different timing segments. Next, we will see what you can monitor and configure for PTPv2 in the RNAO GigaCore software. We already mentioned that clock settings are the group setting in our GigaCore system, so we can go to Configuration and Group Trunk Settings. This will open up a new window where you need to select Groups. Now you can choose the group for which you would like to modify the PTPv2 clock settings. I picked the red group. Next, you will get this window where you need to find the clock settings section. In this section, you will get a drop-down to select the clock mode you would like to use. Clock modes available are end-to-end transparent clock, boundary clock, replicate clock mode, and if you really want to, you can also disable PTPv2 in this group. If you choose boundary clock mode, you can select the profile, the profiles we have seen before, but also you can select auto mode. In auto mode, the boundary clock will automatically recognize which timing values it should use based on the timing of the packets coming in from the grandmaster. If you really want to, you can also use custom mode and modify all parameters like you would like to. Once you select a specific profile, you can also review which parameters are used by that profile. If this configuration is done, you can check which groups have PTPv2 enabled by looking at the PTPv2 icon. So all groups with this little icon in the bottom left corner have PTPv2 enabled. This can be transparent clock mode, boundary clock mode, or replicate clock mode. Next up, there is monitoring. How can I monitor PTPv2 in my GigaCore network? On the left-hand side of the RNAO graph, you can select the PTPv2 overlay. When you enable this overlay, all ports will get a specific icon. We will look more closely at what these icons mean. But first, I would like to highlight that you can also check out IGMP tab for the specific GigaCore and make sure that there are PTP registrations for your PTPv2 devices. If you would like to learn more about IGMP, we already did a webinar on that topic before. So what do all these icons mean? If it's a D, that means that PTPv2 is disabled on that port. A T means end-to-end transparent clock is active on that port. Only for boundary clock and replicate clock mode, we have more clock states. So there is the I for inactive, which means that that link is not doing any PTPv2. There is TR for time receiver. So this port that shows this icon is in the time receiver mode. In this mode, it means that the grandmaster is upstream from this connection. So if you would like to find the grandmaster, go up from the time receiver until you discover the grandmaster. There's also TT for time transmitter mode. So this means that this port is sending out timing information to the downstream device. Finally, there is passive state. In the passive state, this port is receiving timing information, but the device itself is already receiving a better timing information on another port. It's also good to know that you can hover over all these icons. That will also show the port state, and you can see more information about the grandmaster. So in this case, you can see the grandmaster priority, its clock identity, you can see the clock profile and domain being used. Finally, for trunk ports, there is the PTPv2 clock icon, and you can hover over the icon to see the state for every separate group inside that trunk. Next, I would like to highlight some upcoming features which are planned in the next gigacore release, version 1.8.0. First of all, you can make sure that your gigacore can become grandmaster capable if it's in boundary clock mode. So this way, you can have your network as being the grandmaster. No need for special high-end devices that act as your grandmaster. How can you do this? You can go to the web interface, select boundary clock. You have to select a specific clock profile. This will not be possible with auto, because auto, as you might remember, was learning the clock parameters from the grandmaster. But if the switch itself is the grandmaster, you need to specify the profile. If you do this, you can enable grandmaster capable mode and configure the priority 1 value. So this way, your gigacore switches can be the time reference for your whole network. There's also something new in replicate clock mode. In this mode, you can now not only change the clock profile, but you can also override the priority 1 value of your grandmaster. This can be handy in very specific situations. For example, if you have a specific device in this group with a low priority 1 value, and that's therefore not wanting to accept the grandmaster, which has a higher priority 1 value, then you can come in here and override the priority 1 value with a lower value compared to that device, and it will only affect this group. You can leave the grandmaster and all other groups unchanged. So to wrap up some tips, first of all, it's good to know PTPv2 end-to-end transparent clock mode is enabled on all groups by default on the gigacore. You can use boundary clock in larger networks to reduce the load on the grandmaster, but there is not really a reason to completely disable PTPv2, since it's only affecting PTPv2 packets. So even if you're not using PTPv2, you can still leave it enabled. You can use the priority 1 value to determine who will become the grandmaster, and it's always a good idea to also have a secondary grandmaster in case something happens to the first one. Ensure that all switches in your network have PTPv2 enabled or are PTPv2 capable. This can be transparent clock or boundary clock mode. And ensure that all devices in your network, all clocks within the group, have this exact same set of parameters, so the same profile. This includes the domain value as well. It has to be the same, otherwise the devices cannot sync to each other. Next, some debugging tips. As we have seen, you can use RNAO with the PTPv2 overlay to ensure that all ports are in the expected state. You can check out who is the grandmaster for those ports if they are in boundary clock mode. You can use the IGMP monitoring to ensure that PTPv2 multicast registrations are in place. And also ensure that all devices and the boundary clocks within a group are using the same grandmaster or using the same time reference. Some specific devices have an offset graph in their interface, and you can monitor that graph to monitor the clock offset over time. If the clock is very unstable, then this graph will go up and down a lot. If it's a stable clock, then this should be almost a flat line. Finally, there is dedicated software, PTP track count, created by Meinberg, and that you can use that software for more insights into what your network is doing on the PTPv2 level. Finally, here are some references to good information about PTPv2. We have a knowledge base with a specific article on boundary clock and replicate clock. There is the IEEE specification for those who would like to dive really deep, As mentioned, there is PTP account software in the Mindwork blog, and also the Ravenna group has some very interesting information on their website about PTP. Thank you all for joining the webinar. Thank you for watching. I hope you learned something, that you gained some knowledge on PTP, because knowledge is confidence, and confidence only gives you more time to be creative and less time to troubleshoot. Thank you for joining. I hope to see you soon in another webinar. Also check out our other recordings. Thank you. Bye.